Before we get into factorising a monic quadratic expression, let's have a quick look at what a monic quadratic expression looks like. So a quadratic expression is an expression that involves basically a set of variables whose highest power is in fact 2. Okay, so anything that you see that has something squared plus something plus whatever, if the power that you see is no higher than a 2, in fact it's equal to 2, and that is the highest power, then it's quadratic. Okay, so if there's an x cubed, for example here, then it's not quadratic, it's cubic, because the highest power is a 3. So we're only interested in expressions where the highest powers are 2. Now, this one, x² plus bx plus c, so that's the form of what we call a monic quadratic. Monic, mono. Mono meaning 1. It means there's only one term that involves the square of a variable. The numbers that multiply these variables are called coefficients. Okay, so I'm just introducing a little bit of terminology here. So the coefficient of x squared is in fact 1. We don't show the 1, but there is the 1 there. And that's why it's called monic, because the highest power, or the variable that has the highest power, the 2, there's only one of them. Okay, so its coefficient is 1. Now the term in the middle, so this is the coefficient of x, okay, is b. And the constant term, so why it's called the constant term is because there's no variable next to the c. The c is just a number, right? It's fixed, it doesn't change. And that's just called the constant term. Okay, and that's kind of partly the reason why, and this sort of digress a little bit here, but the formula for a linear sort of equation, or a line, is in the form y equals mx plus c, not plus b. Okay, plus c is because c is the constant term. C, it sort of refers to the y-intercept. In fact, when we talk about graphing these particular type of functions, you'll see what I mean. But for now, let's just accept that c is the constant term. So an example of a monic quadratic expression is x squared minus 5x plus 6. Okay, again, notice that the highest power is a 2. Okay, so this is the highest power, and there's only one of this type of variable. So in other words, there's one x squared, I guess, or one type of that term. So it's the same variable, sorry, so it's all in x, but there's only sort of a single x squared term. The x on its own could be whatever number you like, it doesn't matter. And the constant term could be whatever you like. Okay. The main thing is that it's a monic quadratic. Now, why is it called quadratic? Quadratics tend to represent areas, or can be used to represent the area of, for example, a rectangle. And that's why it's in fact called quadratic, because it actually represents the area of a quadrilateral, and the sort of the quadrilaterals that we're talking about here are in fact rectangles. So they're formed by multiplying the sides of a rectangle. So the area is found by multiplying the sides of the rectangle, and the sides of the rectangle can be expressed in terms of a single variable. So in this case, we could represent the width and the length of this rectangle in terms of x. And so multiplying these two together, so these two sides together, so x plus 2 multiplied by x plus 7, so that's length times width, we end up with an expression that represents the area of this shape. So as an example, if we had the width is x plus 2 and the length is x plus 7, okay, so whatever the value of x is, that determines the length, the width and the length. Multiplying those two together, those binomials, you end up with x squared plus 7x plus 2x plus 14, and then collecting the like terms, you end up with x squared plus 9x plus 14. So I guess when we're talking about factorising monic quadratic expressions, we're starting here, but we want to end up here. Okay, so in other words, what's the pattern, what's the rule here, I guess? So what you'll probably know, if you've done this already, then you'll probably know that I need to find sort of two numbers that give you 9, and multiply those same two numbers together to give you sort of the 14. So 2 times 7, right? These two give you 14, but when you add 2 plus 7, it gives you 9. So it's good to notice this already. All right. So I already said this, but we factorise monic quadratic expressions, okay, that are in the form x squared plus bx plus c. B can be positive or negative, by the way. When I say plus b, well, we don't know what b is, but b could be a negative number. We don't know. It doesn't really matter, okay? So we find two numbers, okay, that when you add those two numbers together, you get the b term. Okay, in fact, you get this sort of whole thing there, plus b, and whose product is c. Or it could be positive or it could be negative c. It doesn't matter. Or the constant term could be a negative number. It doesn't matter. Okay, as long as when you pick two numbers, you add them together, you should get b. If you multiply them together, you'll get the c. And remember where that comes from again. Okay, these are the two numbers that we're talking about. So in this example, x² plus 9x plus 14, two numbers that add up to 9. But when you multiply those two numbers, give you 14. Obviously, 2 and 7. We already know this. So this is what we're trying to do. Okay, so a little bit of sort of I wouldn't say trial and error necessarily, but some inspection is necessary. Okay, there are of course more elegant methods of factorising that involve, for example, you could do this with the quadratic formula, but we're not going to introduce that in this video. So we'll keep it simple for now. So let's have a look at 4 examples. Factorise these expressions. So part A, x² minus 7x plus 12. Think of two numbers that when you add them together, you get negative 7, but when you multiply them together, you get positive 12. Now that should give you a clue as to the nature of the two numbers. Okay, so I might just draw the bracket. So we know we've got an x there and an x there. Now, two numbers that multiply to give you a positive 12. They could either be two positive numbers or they could be two negative numbers. Okay, negative times a negative gives you a positive. But they need to add together to give you negative 7. So I think it's fairly obvious here that the two numbers that we're going to find are both negative numbers. So, I don't know, think of two numbers that when you multiply them gives you 12. Think of the factors of 12. So you've got 1 and 12, 2 and 6, 3 and 4, 3 and 4. 3 and 4 gives you 7. So what about negative 3 and negative 4? Okay, so negative 3 and negative 4. If you add those two together, negative 3 plus negative 4 gives you negative 7. I think we're happy with that. Now, if you expand this expression, you should get x² minus 7x plus 12. And you would. X times x is x². Negative 3 times negative 4 gives you positive 12. And then you got x times negative 4, that gives you negative 4x, plus negative 3x gives you negative 7x. So I think we're happy with this one. Okay, what about part B? So x² plus 7x minus 8. Think of two numbers that when you add them together, you get positive 7, but when you multiply them together, you get negative 8. Okay, so multiplying two numbers together to give you a negative, it means one of them has to be a positive, one of the numbers that we're going to choose has to be a negative. Okay, so that's going to be x. So I might just start the solution. So one's going to be negative, one's going to be positive, because a negative times a positive is going to give us a negative. So think of, I guess, the factors of 8 that multiply to give you 8. So we got 2 and 4. Well, 2 and 4, there's no way we're going to get 7 from that. What about 1 and 8? 1 times 8. Or negative 1 times positive 8, for example. Or positive 1 times negative 8. Well, that'll give us negative 8, but we need to choose the correct sign of the two numbers we're going to pick so that when you add them, you get positive 7. So how about we choose positive 8 and negative 1? Positive 8 plus negative 1 gives us positive 7. So we got plus 8x, if you multiply those two together using the extended distributive law, plus 8x minus x, that gives you 7x. So we're happy with that. All right, what about y² minus 2a minus 15? So this one there. Okay. So again, two numbers that when you multiply them together, you get negative 15, but when you add them together, you get negative 2. All right, so I might just draw on this. So I got y and y, negative 15. So it means one of them has to be, one of the numbers we're going to choose has to be positive, one has to be negative. Okay, right. So think of the factors of 15. Okay, again, 15 doesn't have that many, so I got either 1 and 15. So we're talking about whole number factors, integer factors, not decimal factors. Of course, we can extend that to decimals and irrational numbers and surds and all that, but we're just going to keep it simple. We'll just think of integers. What about 3 and 5? Yeah, negative 3 times positive 5. That gives us negative 15. But negative 3 plus 5 gives us positive 2. We want negative 2. All right. So maybe negative 5, positive 3. Negative 5 plus positive 3 gives us negative 2. Okay. Again, if you expand it, y times negative 5 is negative, oops, used the wrong pronumeral there. That should be a y. Sorry about that. And if you've picked up on that already, good, you're paying attention. Excellent. We do this all the time, don't worry. Y times y is y squared. Y times negative 5 is negative 5y, but plus 3y, that gives us negative 2y. Positive 3 times negative 5 gives us negative 15, and we're happy with that. Last one, w squared plus 18w plus 81. All positives, everyone's happy. Everyone's feeling very positive today. So we're going to end up with two brackets that are positive, right? So w plus and w plus. Two numbers that when multiplied gives you 81, but when you add them together, you get 18, all right? And you can sort of think about this a little bit. The factors of 81, well, there's a few there, but how about 9 and 9? Yes, the two factors can be identical, in fact. So 9 plus 9 gives us 18. 9 multiplied by 9 gives us 81. Now, what does this look like to you? This looks like a perfect square, doesn't it? So w plus 9, in fact, all squared. So this is an example of a perfect square that when you expand it, gives you a sort of a quadratic expression. And we've seen these expressions maybe before, so when we looked at expanding perfect squares and factorising perfect squares. So this is really an application of, factorising a quadratic, but it just happens to be a quadratic that's also a perfect square.